Welcome to the course on Python for data analytics, machine learning and generative AI. This session will concentrate on supervised learning and unsupervised learning models that are widely applied in real-world analytics and decision-making systems. Today's session will cover fundamentals of machine learning and its types such as supervised and unsupervised learning, supervised learning models including classification techniques like KNN, SVM, decision tree and random forest. And also it covers distance and similarity measures used in model decision making and unsupervised learning methods such as k-means, clustering, hierarchical clustering and a priori algorithm. We will also see model evaluation metrics and concepts like overfitting and ensemble learning. By the end of this session, learners will be able to understand the core concepts of machine learning, including the difference between supervised and unsupervised learning. You will be gaining knowledge of key algorithms such as KNN, support vector machines, decision trees, and clustering techniques. Machine learning algorithms are broadly categorized into supervised and unsupervised learning. In supervised learning, models are trained using labeled data where the outcome variable is known in advance. This category primarily includes regression models used for predicting continuous values and classification models used for predicting discrete class labels. In contrast, unsupervised learning focuses on discovering hidden patterns in unlabeled data through techniques such as clustering and association rule mining. Classification models are designed to assign observations into predefined categories or classes. Unlike regression, the output variable in classification is categorical in nature. Decision trees follow a hierarchical, rule-based structure. Support vector machine aims to identify a hyperplane and k-nearest neighbor is an instance-based learning method. K-nearest neighbor is often described as a lazy or memory-based learning algorithm. KNN stores the entire training dataset and performs classification at runtime. When a query point is introduced, the algorithm computes distances between the query and all training samples, identifies the k closest point and assigns a class based on majority voting. The intuitive tells me who your neighbors are and logic makes KNN simple to understand, though it can be computationally expensive for large data sets. In machine learning, measuring similarity helps us understand how close or different two data points are. Euclidean and Manhattan distances are geometric measures, ideal for low-dimensional numerical data. Cosine similarity focuses on the angle between vectors, ignoring magnitude and emphasizing direction. Earth mover's distance or EMD measures how much effort it takes to transform one distribution into another. The way we define nearness directly influences how our model behaves and makes decisions. Minkowski distance includes Euclidean and Manhattan variations, commonly used in spatial coordinate systems. Cosine similarity, as we discussed, measures the alignment between vectors, making it powerful for text and document comparison. Correlation, on the other hand, captures similarity in patterns while ignoring scale and offsets. Each metric compares a different notion of similarity: geometry, direction, or pattern. When working with multimedia data like images, standard distance measures may not be sufficient. Earth mover's distance compares image histograms by calculating the work needed to shift mass between distributions. In time series data, symbol distance metrics fail when sequences are misaligned in time. Dynamic time wrapping or DTW aligns sequences by stretching or compressing the timeline. This allows us to compare patterns accurately even when peaks or troughs occur at different moments. Support vector missions focuses on separating classes by maximizing the margin between them. Instead of considering all points equally, SVM pays special attention to the critical boundary points called support vectors. The goal is to find the hyperplane that creates the widest possible separation between classes. A wider margin generally improves generalization and robustness to new data. In essence, SVM is about finding the cleanest and most confident boundary between groups. Sometimes data cannot be separated by a straight line in its original form. In such cases, SVM uses the kernel trick to project data into a higher dimensional space. In that transformed space, complex patterns may become linearly separable. This means we perform a linear operation in feature space that corresponds to a nonlinear boundary in input space. The kernel trick allows powerful classification without explicitly computing higher dimensional coordinates. Now, we will explore the mathematical foundation behind support vector missions. The objective is to minimize the squared magnitude of the weight vector, which maximizes the margin between classes. The constraint ensures that all training points stay outside the margin boundary. Because this is a convex optimization problem, it guarantees a global minimum solution. This means the model finds the best possible separating boundary without getting stuck in local minima. SVMs rely on convex optimization, which guarantees a single global minimum. Neural networks operate in a non-convex landscape and may get trapped in local minima. SVM solutions depend only on support vectors, making them memory efficient. With certain kernels, SVMs can behave similarly to a two-layer perceptron but with stronger mathematical guarantees. Techniques like a priori, k-means and hierarchical clustering fall into the unsupervised label category. And supervised learning uses labeled data to predict future outcomes. Methods such as decision trees, logistic regression, and random forest help make informed predictions. The a priori algorithm is used in market basket analysis. It starts by identifying frequent individual items in transaction data. Then it generates larger candidate items sets step by step. A support threshold is applied to filter out infrequent combinations. This bottom-up approach helps businesses discover meaningful purchasing patterns. We will now introduce k-means clustering for partitioning data into groups. The algorithm begins by initializing cluster centroid randomly. Each data point is assigned to the nearest centroid. The centroids are updated iteratively until convergence is achieved. The goal is to minimize within cluster variance, though choosing the right number of clusters is important. Hierarchical clustering builds structure by grouping data step by step into a tree-like diagram called a dendrogram. In agglomerative clustering, we start with each observation as its own cluster. Clusters are merged iteratively based on similarity. The vertical axis shows the similarity level at which clusters combine. By cutting the dendrogram at a chosen height, we decide how many clusters to keep. Linkage criteria determine how we measure distance between clusters. Single link uses the nearest pair of points but can create long chain clusters. Complete link uses the furthest pair, producing tighter, more compact clusters. Group average linkage takes the average distance between all pairs across clusters. The choice of linkage affects the shape and stability of the final clustering. Decision trees model decisions as a sequence of simple, interpretable rules. We start at the root node and split the data using binary questions. Each internal node represents a feature-based decision. Splits are chosen using criteria like Gini impurity or entropy to reduce uncertainty. The final leaf nodes represent the model's prediction or action. Overfitting happens when a decision tree becomes too complex. Such a tree memorizes noise instead of learning useful patterns. This leads to poor performance on new unseen data. So, pruning removes unnecessary branches from the tree. A pruned tree is simpler and generalizes better. Decision trees are white box models, which means they are easy to understand. They split data step by step based on conditions, and each internal node represents a decision or test. Leaf nodes give the final prediction or decision. The structure works like a clear if then else flowchart. Decision trees choose splits using measures like information gain. Information gain is based on entropy, which measures uncertainty. The goal is to reduce uncertainty after each split. The pi function evaluates how good a split is. It prefers balanced and homogeneous child nodes. Accuracy alone is not enough to evaluate a model. True positives and true negatives show correct predictions. False positives and false negatives show prediction errors. The precision tells us how many predicted positives were correct. Recall and specificity measures how well positives and negatives are identified. A single decision tree is easy to interpret but unstable. Small changes in data can change the tree structure a lot. This makes decision tree prone to overfitting. Random forests combine many trees to improve stability. The ensemble approach gives better and more reliable predictions. Random forest, introduced by Leo Breiman in 2001, is an ensemble learning method based on decision trees. Instead of relying on a single tree, it builds many trees using different random samples of the dataset. This technique, called bagging, selects training examples with replacement to create diverse trees. At each split, only a random subset of features is considered, increasing diversity further. The final prediction is made by majority voting, and as a number of trees increases, the model becomes more stable and resistant to overfitting. The performance of a random forest depends on two key factors: strength and correlation. Strength refers to how accurate each individual tree is. Correlation measures how similar the error of different trees are. For best performance, we want strong trees that make different mistakes. If all trees are highly correlated and make the same error, the forest loses its advantage. Random feature selection plays a crucial role in reducing correlation among trees. By limiting the number of features considered at each split, we introduce useful randomness. Interestingly, using just one or two random features often produces near optimal results. This works because it keeps correlation low while maintaining sufficient strength. This approach, known as random input selection, is a key reason for the success of random forest. Random forest provides an internal validation mechanism called out-of-bag estimation. In each bootstrap sample, about 1/3 of the data is left out of training. These unused samples are called out-of-bag instances. They are passed through trees that did not see them during training to estimate errors. This gives an unbiased estimate of generalization performance without needing a separate test set. Naive Bayes and logistic regression represent two different modeling philosophies. Naive Bayes is a generative model that assumes feature independence. It performs particularly well in high-dimensional problems like text classification. Logistic regression is a discriminative model that directly learns a decision boundary. It does not assume independence and is well suited for understanding feature influence in binary classification task. Let's summarize. This session provides an overview of machine learning, focusing on how models learn from data to make predictions. Key algorithms such as a priori, k-means, decision tree, random forest, naive Bayes, KNN, and support vector machines are discussed. The session also emphasizes the importance of similarity measures and evolution metrics in building effective models. Now, let's start using our Python Jupyter notebook to learn the codings related to all the algorithms. Thank you.